Hello everyone. I want to discuss section 8.4 molecular orbital theory. We will be doing a brief survey of this section. We won't get into all of the details here, but we want to understand that this is an additional model for understanding the way molecules bond. So we'll touch on some highlights here. So the learning objectives we will care about: outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals, describe traits of bonding in anti-bonding molecular orbitals, and then we'll essentially skip the next 2.5. And so I would say understand magnetic properties based on electron behavior as a way of addressing that one. So we've looked at a number of models for how covalent bonds work. We looked at Vesper theory. We looked at valence bond theory. We looked at hybrid atomic orbitals. And this is kind of the last one we'll look at. For many things, it's the best model, but it's a little bit more complicated, and it doesn't work well at predicting some things. It doesn't, when I say work well in this context, what I mean is it doesn't even address, for example, the shapes of molecules, which is one of the important things that we care about. So to set the stage for this, you might remember we talked about the fact that oxygen molecules are magnetic. So let's define what we mean by that. There's actually more than one type of magnetism that something can have. The type of magnetism that we're talking about here is the type of magnetism that you typically think of, which is that something is attracted to a magnetic field. And that is actually technically called paramagnetism. So let's go ahead and highlight that. Something attracted to a magnetic field is paramagnetic. This happens when something has unpaired electrons. So as we've been writing the electron configurations throughout module 6 and 7, whenever we have something with unpaired electrons, what we have is something that is paramagnetic. You may have, as I say that, you may think back to all of those transition metals that had lots of d electrons. So a lot of the magnetism that we associate with metals is because they have unpaired electrons. So they are attracted to a magnetic field. So that's called paramagnetism. There's another type of magnetism. There's actually two other types, but the other one we want to talk about is something being diamagnetic. If electrons are paired, when electrons are paired, something is diamagnetic. Everything has some amount of paired electrons, so we can think of everything as being somewhat but diamagnetic. It's a lesser property, lesser effect than paramagnetism. But when everything is paired up, we have actually a repulsion from a magnetic field. So these properties, it turns out that for oxygen, for the oxygen molecule, that it is paramagnetic. It is attracted to a magnetic field, and that cannot be explained by the models we have already, such as the hybrid atomic orbital theory. We need to have molecular orbital theory to predict that. There's other properties that can only be predicted with molecular orbital theory, but that's the one that is often discussed in this context. So let's talk a little bit about molecular orbital theory. Here's a good comparison between some differences between valence bond theory and molecular orbital theory. The biggest difference is this one. When we think about molecular orbital theory, the word molecular is emphasizing the fact that we're not just treating this as two or more atoms that happen to come together and form a bond. we're treating it as a molecule. The molecule as a whole is going to have orbitals, not individual atoms within the molecule. So that's the big difference here. So instead of, say, taking those atomic orbitals and just hybridizing them, where we're just making kind of a brief shift and then we look at an overlap, we're combining all of the orbitals from all of the atoms to make molecular orbitals that are for the molecule as a whole. And so that's the difference. We talked about sigma and pi bonds. What we'll see here is that we still have sigma and pi bonds, but they have other possibilities here, because we can talk about bonding and anti-bonding interactions in the molecular orbitals that we form here. And we cannot predict shapes with molecular orbital theory. It doesn't do that. But it can predict where the electrons are within a molecule. One of the downsides with the valence bond theory is that we kind of see that the resonance way of representing things doesn't work very well. And it turns out the molecular orbital theory does a much better job of explaining that when that happens. Now, that is something that is kind of well beyond like answering that question is well beyond the scope of this course. That's something you would see in an organic chemistry course. But just understand that that is another reason why molecular orbital theory is often better for some things than some of these other ones we've talked about. Okay, so let's talk about what molecular orbital theory is about. So again, instead of thinking of the orbitals as places on atoms that then overlap, we're kind of deconstructing the whole thing and saying, what if we think about those orbitals as being part of the molecule instead of part of the orbitals themselves? So we come up with what are called molecular orbitals, and we are going to still have this idea of the linear combination of atomic orbitals, and that we take all of the atomic orbitals and we combine them together into molecular orbitals. And we have the same number of orbitals in the molecule as we did within those atoms. And to understand how this works, we again need to remember that electrons are waves and how those waves interact. And we hinted at this in a previous video, but I want to kind of spell it out a little bit more succinctly here in terms of what ends up happening. So we can have waves combined in a couple of ways. One is that they add together and get bigger. Okay, so we have, this is called constructive interference. The waves kind of are on top of each other in a way that the whole thing gets bigger. Another way that waves can combine is with what we call destructive interference, and this is when they are opposite of each other. So basically one wave cancels out the other when they're out of phase. So we call this destructive interference. So they can combine to be bigger, or they can combine to be basically canceling each other out. And these different possible combinations represent what we see in terms of molecular orbitals. So how are they combining? Are they combining to be more stable, or are they combining to be less stable? So we essentially have these two possibilities. So what we do is we call these two possibilities bonding or anti-bonding. So when they combine in such a way that they are more stable, we call that a bonding orbital. When they combine in a way that they are less stable, we call that an anti-bonding orbital. Let's look at some examples of that down here. So if we have two, just starting with s orbitals, and we combine those with molecular orbital theory, we would think of this as making two possibilities: a bonding orbital, where the the waves are combining in a way that is more stable. So we call this sigma with a subscript s. The s is indicating that we're looking at s orbitals that are combining. And then the anti-bonding orbital, we have sigma subscript s and then a star on it. We often use the star in chemistry to represent something that has a high energy or has more energy than it should have. So anti-bonding orbitals are less stable. They have more energy than they should have. And the reason is because they're combining in a way that is actually less stable than what you started with. So you end up with basically a node here between the nuclei. So in the anti-bonding orbitals, you always have one additional node to what you would have in the bonding orbitals. Again, you start with 2 orbitals, you end with 2 orbitals. So that's the idea of the combination of atomic orbitals, the linear combination. Here we're looking at an additional option, additional possibility to represent what's going on with molecular orbital theory. So here we're showing the combination of p orbitals to form a sigma bond. And what you'll notice here is that this is, again, we talked about this previously, but we're using the colors here to show the different signs of the wave function, which you don't have to know which is which in terms of red or blue, but essentially you want red with red to have constructive interference, blue with blue to have constructive interference. So that's what we're showing here. When we have the reds overlap, we end up with this giant bonding orbital, and we call that sigma, and then subscript px. And what that means is it's a sigma bond, and it's a p orbital. The x is essentially showing that they're kind of aligning together, like we're showing there. The other possibility is what we're showing down here, where the overlap is with orbitals of opposite signs. So blue and red here, they don't combine, and we have an anti-bonding orbital. So you've got the node between there, so you've got a smaller lobe node between them, higher energy anti-bonding orbital that we would form there. Again, we have 2 orbitals that combine to form 2 molecular orbitals. We can also use molecular orbital theory to describe pi bonds. So here we're looking at some pi bonding molecular orbitals and anti-bonding as well. So what we're showing here is that they are of the same sign. The signs kind of match up, and we get this. We get a pi bond where we've got a lobe above the internuclear axis and a lobe below the internuclear axis, where each of the lobes are of the same sign. So the red with red, blue with blue. And then for the anti-bonding, this is where we have the opposite signs kind of lined up. So red with blue, blue with red. And then we get a node between, and we have these kind of are sort of tilting away instead of tilting towards each other. So this is a sigma star, which is an anti-bonding orbital, and a sigma, which is a bonding orbital. And then the subscript of p in each case is telling us that we have p orbitals there that are overlapping. And this p could be either y or z. It doesn't really matter that we label that. So we could have, if you think back to when we discussed the triple bond, we could have, so I said, y or z, you could have, 2 pi bonds within a single molecule if it were a triple bond, right? So we know how that would work. And this is just discussing all of those possibilities. Okay, so I think that's as much as we need to go with this idea. So you want to understand molecular orbitals in terms of the general concept of sharing throughout the molecule, the fact that you have these sort of opposite signs going on, antibonding and bonding possibilities as a way of describing it. This gets into the details of drawing the electron configurations for these, which is something I think we can hold off on. This will become important if you take additional chemistry courses, and it's a good way of understanding what's going on here from that standpoint. But it gets, you can see it gets really complicated here. So we'll go ahead and leave off there, and that concludes Module 8.